In mathematics, the integral test for convergence is a method used to test infinite series of non-negative terms for convergence. It was developed by Colin, Maclaurin and Augustin-Louis Cauchy and is sometimes known as the Maclaurin-Cauchy test. Statement of the test. Consider an integer n and a non-negative continuous function f defined on the unbounded interval n infinity, on which it is monotone decreasing. Then the infinite series n equals n infinity f n display style sum underscore n equals n caret inf d f n closing curly bracket converges to a real number if and only if the improper integral n infinity f x d x display style int underscore n caret inf d f x backslash dx is finite. In other words, if the integral diverges, then the series diverges as well. Remark: if the improper integral is finite, then the proof also gives the lower and upper bounds for the infinite series proof. The proof basically uses the comparison test, comparing the term f n with the integral of f over the intervals n-1, n, and n+1, respectively. Since f is a monotone decreasing function, we know that f x f n for all x n infinity display style f x leq f n quad text for all x in n inf d closing curly bracket and f n f x for all x n display style f n leq f x quad text for all x in n closing curly bracket. Hence, for every integer n and for every integer n plus 1, by summation over all n from n to some larger integer m, we get from 2 n m plus 1 f x d x equals n m plus 1 f x d x f n equals n m f n display style int underscore n caret m plus 1 f x backslash dx equals sum underscore n equals n caret m underbrace int underscore n caret n plus 1 f x backslash dx underscore leq f n leq sum underscore n equals n caret m f n closing curly bracket, and from 3 n equals n m f n f n plus n equals n plus 1 m n minus 1 n f x d x f n equals f n plus n m f x d x display style sum underscore n equals n caret m f n leq f n plus sum underscore n equals n plus 1 caret m underbrace int underscore n 1 caret n f x backslash dx underscore geq f n equals f n plus int underscore n caret m f x backslash dx closing curly bracket. Combining these two estimates yields n m plus 1 f x d x n equals n m f n f n plus n m f x d x display style int underscore n caret m plus 1 f x backslash dx leq sum underscore n equals n caret m f n leq f n plus int underscore n caret m f x backslash dx closing curly bracket, letting m tend to infinity. The bounds in 1 and the result follow. Applications: the harmonic series n equals 1 infinity 1 n display style sum underscore n equals 1 caret inf d frac 1 n diverges because, using the natural logarithm, its derivative, and the fundamental theorem of calculus, we get 1 m 1 n d n equals lane n pipe 1 m equals lane m infinity 4 m infinity display style int underscore 1 caret m frac 1 n dn equals lane n bigger underscore 1 caret m equals lane m2 inf d got text 4 m2 inf d closing curly bracket. Contrary, the series zeta 1 plus epsilon equals x equals 1 infinity 1 x 1 plus epsilon display style zeta 1 plus var epsilon equals sum underscore x equals 1 caret inf d frac 1 x caret 1 plus var epsilon. Cf. Riemann zeta function converges for every epsilon greater than 0, because by the power rule 1 m 1 x 1 plus epsilon d x equals minus 1 epsilon x epsilon pipe 1 m equals 1 epsilon 1 minus 1 m epsilon 1 epsilon less than infinity for all m 1 display style int underscore 1 caret m frac 1 x caret 1 plus var epsilon dx equals frac 1 var epsilon x caret var epsilon bigger underscore 1 caret m equals frac 1 var epsilon bigl 1 frac 1 m caret var epsilon bigger leq frac 1 var epsilon less than inf d got text for all m geq 1 closing curly bracket. From 1 we get the upper estimate zeta 1 plus epsilon equals x equals 1 infinity 1 x 1 plus epsilon 1 plus epsilon epsilon display style zeta 1 plus var epsilon equals sum underscore x equals 1 caret inf d frac 1 x caret 1 plus var epsilon leq frac 1 plus var epsilon closing curly bracket, which can be compared with some of the particular values of Riemann zeta function, borderline between divergence and convergence. The above examples involving the harmonic series raise the question whether there are monotone sequences such that f n decreases to 0 faster than 1 n but slower than 1 n 1 plus epsilon, in the sense that lim n infinity f n 1 slash n equals 0 and lim n infinity f n 1 slash n 1 plus epsilon equals infinity. Display style lim underscore n 2 inf d frac f n 1 n equals 0 got text and got lim underscore n 2 inf d frac f n 1 n caret 1 plus var epsilon equals inf d for every epsilon greater than 0, and whether the corresponding series of the f n still diverges. once such a sequence is found. A similar question can be asked with f n taking the role of 1 n, and so on. In this way it is possible to investigate the borderline between divergence and convergence of infinite series. Using the integral test for convergence, one can show, see below, that, for every natural number k, the series still diverges. Cf. Proof that the sum of the reciprocals of the primes diverges for k equals 1, but converges for every epsilon greater than 0. Here lnk denotes the k-fold composition of the natural logarithm defined recursively by lane k x equals opening curly bracket lane x 4 k equals 1 lane k minus 1 x 4 k 2 display style lane underscore k x equals begin cases lane x and text 4 k equals 1 lane underscore k 1 x and text 4 k geq 2 end cases. Furthermore, nk denotes the smallest natural number such that the k-fold composition is well defined in lnk. nk 1 I e n k e k e single quote s equals e k display style n underscore k geq underbrace e caret c dot caret e underscore k e text s equals e up arrow k using tetration and uths up arrow notation to see the divergence of the series. 4. Using the integral test, note that by repeated application of the chain rule, d x lane k plus 1 x equals d x lane k x equals 1 lane k x d x lane k x equals 1 x lane k x display style frac d dx lane underscore k plus 1 x equals frac d dx lane underscore k x equals frac 1 lane underscore k x frac d dx lane underscore k x equals c dots equals frac 1 x lane x c dots lane underscore k x closing curly bracket hence n k infinity d x lane k x equals lane k plus 1 x pipe n k infinity equals infinity display style int underscore n underscore k caret inf d frac dx x lane x c dots lane underscore k x equals lane underscore k plus 1 x bigger underscore n underscore k caret inf d equals inf d closing curly bracket to see the convergence of the series. 5. Note that by the power rule, the chain rule in the above result, minus d x 1 epsilon lane k x epsilon equals 1 lane k x 1 plus epsilon d x lane k x equals 1 x lane k minus 1 x lane k x 1 plus epsilon display style frac d dx frac 1 var epsilon lane underscore k x caret var epsilon equals frac 1 lane underscore k x caret 1 plus var epsilon frac d dx lane underscore k x equals c dots equals frac 1 x lane x c dots lane underscore k1 x lane underscore k x caret 1 plus var epsilon closing curly bracket. Hence n k infinity d x x lane k minus 1 x lane k x 1 plus epsilon equals minus 1 epsilon lane k x epsilon pipe n k infinity less than infinity. Display style int underscore n underscore k caret inf d frac dx x lane x c dots lane underscore k1 x lane underscore k x caret 1 plus var epsilon equals frac 1 var epsilon lane underscore k x caret var epsilon bigger underscore n underscore k caret inf d less than inf d and 1 gives bounds for the infinite series in 5. References: Knopp, Conrad, Infinite Sequences and Series. Dover Publications, Inc., New York, 1956. Section 3.3. ISBN 0-486-60153-6. Whitaker, E. T. and Watson, G. N. A Course in Modern Analysis. 4th edition. Cambridge University Press. 1963. Section 4.43. ISBN 0-521-58807-3. Ferreira, Jamie Campos. Ed. Calaus de Gulbenkian. 1987. ISBN 972-31-0179-3.